Hi, and welcome back to a gentle introduction to LLMs. This is part one officially, where we start getting into the meat of what LLMs are and how we can use them and how to train them, how to program them. We'll begin with the tokenizer. Why the tokenizer? Well, let's take a look at a pipeline, whether it's for training or for inference, it pretty much is the same. The way it works is you take some string, some natural language, some text, you feed it into a tokenizer, this mysterious thing. It translates the text into numbers because computers, they don't know text, they don't know pictures, all they know is numbers. So whenever you want to use AI, we need to translate into computer language, which is numbers. Then these numbers go through an embedding layer, which basically maps each of these numbers to a series of other numbers. So for example, here it mapped 59 to 0.4, minus 1.2, 0.1, and so on. And it mapped 20 to 0.3, 2.5, minus 2.5, and so on. Then for a number of times, you will run a transformer block. Pretty much every model looks like this, whether it's ChatGPT, whether it's Claude, they all have this look, and the entire pipeline basically looks like this. So this is very model agnostic. You'll have each time a different number of transformer blocks. In this case, it's only 3, but you can have something that goes deeper into 20, 30, 100 transformer blocks. For visualization purposes, I stuck to only 3. And we can see how each transformer block takes these numbers and then does some stuff to them and outputs like some slightly different numbers. For example, took 0.4, made it 0.2, took minus 1.1, took 0.1, although it operates on the entire sequence. So I took this sequence and made it into this sequence, took this sequence and made it into this sequence. And then each of the transformer blocks, they're different internally, although they work the same manner. They have different internal numbers, which dictate how they change the incoming numbers. So we can see that it outputs these things. And then on the final transformer block, you go to a de-embedding layer, which is basically the opposite of an embedding layer. It will take these hidden representations, as we call them, and it will map it to the vocabulary. You'll see what is the vocabulary in a second. It will basically tell you for each token which word in the vocabulary is most likely that this is. For example, here it seems that it's very likely it's this, whatever this is, and here it's this, whatever this is. And then you will do some sampling on top of these numbers, and you will get numbers in the end, in this case 20 and 33, which you will then run to the tokenizer, which will detokenize your numbers into a text. So it will take 20, 33 and translate them into world !I. This pretty much is how every LLM works. So let's take a look at what this tokenizer is. I think it's kind of clear. It takes natural language or text and transforms it into numbers. For example, it translates hello world into 5920. Takes hello, makes it 59, takes space, world, and makes it 20, because there's also the space and the exclamation mark as well. Different text should be translated to roughly different numberings. So hi world becomes 3920 in this case. Of course, different tokenizers can operate on different level of granularity. For example, here we have basically one word per token, right? 59 hello, 20 space world. But you can have a different tokenizer that takes the same text and makes it into hell or world exclamation mark. Like these are the numbers that it has, and internally 13 represents hell, 40, 0, 10 world, 31 exclamation mark. These numbers are somewhat arbitrary. I just chose them for visualization purposes. But tokenizers do end up with these sequences. So if you ever take a look inside of a tokenizer, inside of its vocabulary, you'll see basically this mapping. So it's basically one big JSON mapping table that says, okay, given some string, to which integer it maps to. Different strings should map to different integers. There should be no repetition on this side, but there can be some repetition on this side, and we'll take a look a little bit later what this means. But for example, this tokenizer takes hello and translates it to 9419. Takes VT and makes it 9420. Takes whatever, some character, articles into 9421. So for example, particles would be whatever P is, articles 9421. That's how tokenizer works. They're basically internally a lookup table with some extra processing done on top. We already said what a vocabulary is. It's basically all string to integer representations. They're usually huge. It can be in the orders of 200,000 for modern models. And it's basically an efficiency trade-off, because if you have a larger vocabulary size, you can output more tokens per word, meaning you have like slightly more efficiency. While if you have a smaller vocabulary size, for example, each token is one character, you end up having to create more tokens in order to represent one word. For example, let's take the word representation, which the Qwen tokenizer represents as 83116. And let's take some made-up tokenizer that does one character per token. So it takes R, makes it into a token, takes C into a token, yada yada. It would be this very long sequence, both the same word, just different tokenizers. But we can see that if we were to do LLM inference, which does one token, it basically generates one token at a time. If you have this tokenizer, it will basically generate the word representation in one go. While if you had this tokenizer here, it will generate it in 3, 6, 9, 12, 14 passes. So it'll be 14 times as slow, basically, hurting a lot your efficiency. Let's try to make some tokenizer stuff here very quickly in our code. We will begin by first importing the relevant library. So specifically from the module transformers that we downloaded last time, we will import auto-tokenizer. That is basically a class that wraps all tokenizers that Hugging Face has into one representation, so you can load all tokenizers in basically one line. If you want to know what Hugging Face is, I'll link in the description, but it's basically this massive community project where people share their models, people share tokenizers, big companies open source their models, and you can get access to them by just downloading them directly. It's made very easy. It's basically become the de facto standard when working with transformers. In our case, we only care about tokenizers for now, so we'll take this tokenizer, and then we need to load our tokenizer. We need to make it. Let's make a variable called tokenizer, and then it will represent a tokenizer. So we'll take this class tokenizer, and then we'll do from pre-trained. That basically tells the library, I won't be making a tokenizer from scratch. It already exists. It's already been trained, loaded into here. Now you can pass a directory, or you can pass something online from this Hugging Face website that I linked. We'll be mostly dealing with the Qwen models. So from the Qwen provider, the Qwen 3 version of models, and specifically the 0.6b model size. Now this model is big enough that you can get like some meaningful outputs from, but small enough that you can run it on a GPU of only 4 gigabytes VRAM for inference. So a lot of you will be able to play around with these models for inference on your small local machines. Now let's try to tokenize some stuff by running, let's print them out, whatever it outputs. We tokenize things by running tokenizer.encode. So this encodes them, tokenizes them. And then here we have to pass whatever string we want. Let's start with hello world. Let's save. And then let's, in our terminal that we set up from before, run this file, in which case I've called it tokenizer tests. Right, let's just run it here. And let's see what output we get. It will first download the tokenizer from the internet, and it will load it. It will tokenize hello world as 9707433370. And let's try to detokenize these tokens to see how the tokenizer sees the underlying data by running tokenizer.decode. And here we need to pass a list of integers. Since we want to do them one at a time, we'll pass 9707 first. Then we will do, let's copy it 3 times so we don't have to write it each time. I'll do 4337 for the token. And then finally we'll see what the token 0 represents. And then if we run our program again, we will first see the tokenized text. And then for each of these, we will see the detokenized text. For example, 9707, that's hello. 4337, right here that we detokenized is space world. And finally 0 is just the exclamation mark. We can play around with these things. We can try to tokenize some more stuff. Let's comment this out so it doesn't pollute our outputs. Let's try to detokenize, I don't know, gentle introduction, misspelled, introduction to LLMs. See how the model sees this text. A Qwen model would see it as numbers. It will see basically this long string of text. Maybe something interesting, what happens if you have spelling mistakes. Let's see, as I did a space here. Maybe I write something like this. I flip these 2 characters. Let's see how the 2 texts would compare when tokenized. Give it a second to load the tokenizer. We can see the text become very drastically different. The last 3 kind of match. Then these don't match, these don't match. Basically only the last 3 tokens match. So I believe the 2 LLMs. We can see what exactly tokens these are by running again the decode step. Tokenizer. Basically right now we're playing with the tokenizer. We're trying to experiment what a tokenizer is and try to familiarize ourselves with some programming stuff. Tokenizer decode. Then finally tokenizer.decode 82. So let's see what each of these tokens represent by running again the program. You can see what each of these tokens corresponds to. So, okay, so space L is 444, then LM is this large number. And then finally, just the S is 82. So we can see how these two changes basically reinterpreted the previous text completely. This kind of nicely segues into some issues with tokenizers. They're non-bijective, so meaning two sequences of tokens can map to the same string. Let's take a look here real quick. We can make a very easy contrived example by tokenizing hell and then tokenizing O. So hell O into two separate tokens and force the model to interpret it like that. Let's run our tokenizer test again. And we can see, okay, these two tokens. So if we were to detokenize 9707, which was hello as we saw previously, and we also detokenize the two tokens 80294 and then 78. So these two tokens together back to back. Let's see what the tokenizer would interpret them as. And yes, as expected, it will see both as hello. So to a human, these two things would be equivalent, but from the model's perspective, these two things are apples and stars. Completely different text, completely different numbers. Now, models are trained with enough data that they are kind of robust against such things. However, some issues can arise out of this. And then the second issue is that they can be lossy, meaning some information can be lost. This is why, for example, if you remember back in the day, there was a huge kind of funny meme where people were asking how many R's are in a strawberry. The root of the issue is that models don't see the word strawberry. They see just some numbers. And we can see how it interprets the word strawberry into tokens, but it never sees the R's individually. So for a model, let's see the last line. It sees strawberry as 49567 to 15357. So there's no information on how many R's there are. This gets lost a bit to the model. So some of these fine-grained questions, also if you make up a word, for example, ragara, right, and you ask it, okay, how many R's are in there? The model has no idea. It just sees tokens, so it can make mistakes. This gets especially problematic when we start talking about math. Let's comment these things out again, because as you can see, two very similar numbers. Let's take 2.39999, and then let's take basically what humans would round it up to 2.4. And then some humans actually, in some cultures, they use instead of a punctuation, a comma. They will write it out like this. So these three texts for a human, pretty much they would be the same, but for a model, they would be very different. You can see they start the same here, because of the comma and the period, things are different. But then one is interpreted as this very long sequence of numbers, while this is a very short sequence of numbers. For a model, it might get confused based on this, hence why models make math mistakes. Now, this also shows you why models might struggle a bit with math, not just by making mistakes, but in terms of time to generate outputs, because you can see that each number, each digit is a token, meaning that in order to generate this very long number, which for humans is basically 2.4, a model would take 3, 6, 9, almost 3 times as long as it would take to generate 2.4, because each number is a different token. So whenever you have models generating math solutions or just generating numbers, they tend to be a little bit slower because they need to generate each digit at a time, rather than with words where they can generate the entire word in pretty much 1 or 2 tokens. So math tends to slow down models. That basically concludes all there is to talk about tokenizers. When we talk about training, we'll see how to train tokenizers, how to fit them on data. But for now, this is all we need to know when we want to experiment with inference. As always, if you have any questions, don't hesitate to post them in the comments. I will be answering questions as actively as I can.